Hello, this is Hideo Kobayashi. Let's get started. And today, I'm going to explain about control theory, control engineering. So let's move on to today's material. So welcome to my broadcasting. This is Kobayashi, YouTube University of Science and Technology. My name is Hideo Kobayashi. I run my company named iTop Company Limited in Japan. It's an engineering consulting company. And also I'm doing a lecturer at technical seminars, math seminars, technical English seminars, and so on. And today is the second delivery in total. So today I'm going to explain about control engineering, number 1. This is for undergraduate students. And today's topic is proportion, integration, and differentiation control in control engineering. Okay. And also, I'm also doing a part-time lecturer at Graduate School of Nagoya University. This broadcasting is from Odawara City, Kanagawa Prefecture, Japan, to the world. Okay, I'm going to next slide. So today I'm going to explain about control theory, classical control theory. In another word, this is set. PID control. Okay, from the beginning, I'm going to explain. Number 1, classification of control theory. We have several kinds of control theory. The most basic control theory is 101, classical control theory. This is also called PID control. P means proportional, I means integration, D means differentiation. Okay. 102, modern control theory. 103, postmodern control theory. 104, adaptive control theory. 105, other control theories. Today, I'm going to explain about the first stage of the 101, classical control theory, okay? This is a classical, but this control theory is used widely in the world up until now. Okay. Next slide. And what is classical control theory? Okay. So, classical control theory, in another word, PID control theory, is in the figure like this. It's a one input-output system. Input is only one, output is only one, okay? So the control object, okay? This is in control engineering, this is set, a plant usually. So input is given and to a control object. And then control object gives output, okay? This system, one input, one output, and control object, okay? This system is called one input, one output system. Okay, so the classical control theory is adapted for this system. Okay, only one input and only one output in this system. Okay, as I explained, I confirm here again, three varieties in classical control. One, proportional control. So this is called P control. Number two, integral control. So this is called I control. Number three, differential control. So this is called D control. Okay. So when we use proportional control only, in this case, this control is called P control. Okay. When we use P control and I control at the same time, in this case, this control system is called PI control system. So when we use P control, I control, and D control at the same time, in this case, this PID control system, this system is called PID control system. Okay, so when we use this classical control theory, so one pattern is proportional control only. Okay, second pattern is PI control system. Third pattern is PID control system. These are the classification and judging from actual control. Okay, then we go to next slide. Okay, I'd like you to refer to the upper flow. Here, XT is an input, okay? ET is error. And this is PID, each controller, okay? And also here, control object. This is also called plant in control engineering, okay? Then YT is usually output. Then this is usually feedback, okay? Negative feedback. So here, minus sign is used, okay? So P is, as I explained, proportional. Proportional means ET, error, times KP, proportional gain. We call it proportional gain. I control is an integration. So the this error is integrated, and coefficient KI, integrated coefficient. And D control, differential control. So ET is differentiated like this by T, okay? And KD is a differential coefficient. In other words, we can call it differential gain, okay? So when we use P control only, this flow goes like this, then comes to the plant, then output, okay? But when we use PI control system, then we use this flow and this flow at the same time. Then two comes here, and then object is control, okay? When we use PID control at the same time, then we use this flow, and this flow at the same time. Then we can control the object, okay? So when we see this flowchart from the control diagram for each one. This is lower figure, okay? This axis is time. This axis is output, YT here, okay? So when we do P control only, P control, okay? P control here, blue one, blue control, okay? So the input is R. Here, input is also called reference. So R, the character R is used. This is same as XT here, okay? P control only. We control like this blue one. So we always have, in this case, steady state error, okay? So we always have steady state error, P control only. So that we accumulate steady state error. So this accumulation is made integration. Then we do the control of PI control, P control and I control at the same time. Then, okay, we can get red line, red curve, okay? Then here, we don't have now steady state error, okay? So usually, we don't use P control only. At least we use PI control, okay? And also, we can use PID control at the same time. And then PID control, this green one, PID control, okay? So compared with the red curve shows PI control. And by PID control, the response is fast compared with PI control. So in response time, PID control is better. It's faster compared with PI control. Okay, this is the difference between PID control and PI control. Okay. Then we go into next slide. So what's P control in theory? So theory is expressed by math, okay, formulas. So here, P control, UT is here, this one, okay? UT is given like this, input minus output, and this becomes error, and times KP, okay? The XT minus YT is ET. So P control is expressed as this formula, number one formula, okay? So usually in PID control system, we use Laplace transform, and also Fourier transform. Fourier transform is now written here. And also, how to do Laplace transform is also, it's not written here. I'm going to explain later in another lecture. Okay. The time schedule for to do Laplace transform explanation is not still in the air. It's still in the air. Okay. But when we apply Laplace transform to number one formula, then we can get No.2 formula. Okay, this becomes like this. So as for the detail, I'll explain as I say now. In another lecture, I'm going to explain. But parameter t becomes S parameter. This is the characteristics of Laplace transform. As for the detail, later in the other lecture. Okay. So number 4, what's PI control? PI control, as I said, P control and I control are used at the same time. Now here, P control, here, I control, okay? So we can write like this from number 3 formula to number 4 formula. Here, we use this integration time, Ti. Then, using Ti, we rewrite number 3 formula to number 4 formula, like this. So number 4 formula is changed using a Laplace transform. Then we can get number 5 formula, like this. Okay? So the integration, in time integration, okay? Then this is transformed, Laplace transformed. Then integration becomes 1 over S. Integration becomes 1 over S in Laplace transform. So here, 1 over S appears. And next slide. What's PID control? P, I, and D are used at the same time. And this is P control. This is I control. This is D control. Okay? Then we use TD, derivative time, TD. Then using this TD, we use TD to the formula 6. Then we can get formula 7 like this. Sorry, and this equation using TD. And then this is Laplace transformed. Then we can get formula 8. Okay. So differentiation becomes S by Laplace transformation. Okay. Then next page. General control method for a classical control theory. Usually, this control theory is used in negative feedback system. Okay, negative control system, negative feedback control. Okay, reference value. This is also called input and error. And this one minus this one. Output is caught by sensor. The sensor signal comes to this as a negative feedback signal. Okay, and controller. This controller means P controller or PI controller or PID controller. Then the plant, a plant is controlled. Disturbance. We usually have electrical disturbance or something like that. Okay. Then output is also called actual state. Then this actual state is sensed by the sensor. Then this signal is going to the signal as a negative feedback. I write here sensor, but usually we can also write gain, feedback gain, instead of writing sensor. Okay. So Today's lecture is to this page. Okay, thank you for today. That's all for today. Okay, thank you. See you next time.